Okay. So now I've started recording. Okay, and now we can start the discussion. Okay, of the lectures. Okay. Uh, in the previous lecture, we actually go over the minimax algorithm. Okay. So as to make sure everyone get the idea, I will actually go over the concept of the minimax algorithm again, with some more example with some more examples. Okay, so essentially, the first concept we need to establish is that when we want to create an AI for playing the game, okay, the AI itself need to be able to handle different kinds of chess games. Okay, so in order to make this happen, in order to facilitate the creation of an AI that can be used on different kinds of chess games, we again need to introduce the concept of abstraction. Okay, so the whole idea is that different chess games actually have different winning scenarios. Okay, so I believe that you may not play chess. Okay, or you may not play the Go. Okay, Go chess. Okay, but you know that different chess game, different board games, and different kinds of games. Okay, they have different winning scenarios. Okay, okay. So let's take a look on the chess. Okay, if you are able to make the opponent's king, okay, or if you are able to make your opponent's king chess pieces in great danger, okay, and he cannot escape from that danger, you will say that it's checkmate, and then the game will end. Okay, but in the Go chess, all the chess pieces are the same. Okay, it doesn't have the different variety of the chess pieces in the chess game. Okay, so in the Go chess, okay, what you will do is after going through the game, okay, when both players, okay, uh, cannot make further movement, okay, then you actually count the score of both players, and the player who get a higher score win. Okay, okay. So in Go chess is 圍棋, okay, you will actually count the you will actually do the counting on the winning points of both players. Okay, and then the player that gains the highest winning points will win. Okay, so this is the concept of the Go chess. Okay, and it has a very different winning condition as the chess. Okay, so if you do not find a way to abstract the idea of winning, then you cannot write a AI who play games. Okay, okay. We need to find a common representation that allow us to write an AI to play different kinds of chess. And we actually introduce this score. Okay, we artificially create a score that if the score equal to 0, then both players have a draw. If the score is getting closer to positive infinity, that means that the player one is winning with infinite advantages. Okay, so if the player is closer to 0, that means that the player is winning with a marginal advantage. If the player is getting closer to infinity, that means that the player is gaining a infinite advantage. Okay? And the positive and the negative side are assigned to one of the players. Player 1 is assigned with positive, and player 2 is assigned with negative. Okay? So under this scheme, okay, if player one wants to win, what it needs to do? If player one needs to win, what it needs to do? Anyone? If player one need to win under this scheme, under this score representation, what it needs to do? It needs to maximize the score, right? If the player one max keep on increasing the score, then the score is getting closer to positive infinity that will win a higher advantage. On the other hand, if player two is trying its best to minimize its score, then the player two will win with a higher advantage. Because for player two to win, with a infinite advantages in the score need to be close to negative infinity. Okay, so as the score decreasing, the player two with a high advantages. If the score is increasing, the player one has a high advantages. Okay, so in this game, you have a player that will try to maximize the score, and you have another player who will try to minimize the score. The behavior of the player is defined after we define the score for evaluating the output of the game. Okay, we have the measurement first, and then the measurement becomes the KPI, and we can use the KPI to define the behavior of the players. Okay, just like if you are working in a company, okay, when you are doing when you're doing your job, okay, you will also take a look on your KPI and then adjust yourself to the KPI, okay? So in this game, okay, player one's KPI is to maximize the score because for player one to win, is KPI is that if you have an even score, if the score of the game is infinitely positive, then it will win with an infinite advantage. Okay? If the score is having infinite negative, then the player two will have advantages. Okay, so player two's KPI is to reduce the score, and the player one's KPI is to increase the score. Okay, so that is why in the algorithm you will have the max player and the min player. The max player are referring to a player who will maximize the output of the game. The min player is referring to a player who will minimize the score of the game. Okay, the max player and the min player is actually defined by our score definition. We have the score definition first, and then we derive the behavior of the two players from this definition. Okay? Okay. So after we define the definition, okay, and the rest is very simple, okay? The state of the game is essentially the positioning of the chess pieces. The operator is defined the number of legit moves, okay? And the terminal test is actually checking whether the game is already reached the end of the game. And the utility function is given the numerical output of the game. Okay? And what we want to do next is to create the so-called search tree. Okay? The whole idea here is that we just simulate all the possible outcomes. We just simulate all the possible outcomes of the game. Okay, so we actually talked about this in the previous lecture. Is that when you want to do decision, this is the simplest and most logical way to do decision. Okay, I write down for each decision making step. I write all the outcome, and under all the outcome, if there is new decision I need to make, I also list out all the decisions that I can make. I can list out all the outcomes, and I can do it over and over again. And ultimately, I will list out all the possible combinations of the outcomes under different combinations of the decisions. Okay, so as you can see here, if you are in a company, if you want to increase the sales and the profit, you can choose advertising company or expand the sales employee team. or if you choose to extend the advertising, then you can choose new agencies or work with existing agencies. If under both choices, you also have different choices of increasing budget. So all these different decision combination will generate different outcome at the end. And in a search decision, the decision making tree like this, I just list out all the or list out all the possible outcome, and I select the one that will make me the best. Okay, so this is the so-called decision making tree. Okay, and I think it is very logical, right? It is something you actually do decision making using this scheme, right? If you have the time, okay. If I have the time, if I want to do decision logically, I would just list out all the possible decisions that I can make. And then under each decision making combination, I try to compute the outcome. I try to do some simulation and get the outcome. And then I choose the one that will make me gain the most. Okay, make me gain the most. Okay. So in the search tree, we are actually bringing this paradigm into our process, okay? So here is the tic-tac-toe that is called in Cantonese days 第一個三關, okay? So in the tic-tac-toe, essentially, we start off with a empty state, okay, where no X and O is being put, okay? And without the loss of generosity, we just assume the max player is the first player who will make the move, okay? And the max player will actually place the X sign in the chest, okay? He is assigned to put the X sign, okay? So there are 8 possible cells in the initial chessboard of the tic-tac-toe. There are actually 9 different spots that the 9 different cells that the max player can play the X symbol, okay? And what it does is what we need to do is to list out all these outcomes. Okay? List out all these outcomes, okay? And after listing out these outcomes, okay, we actually don't know whether we are going to win or not. So we keep on our deduction process, okay? So for the leftmost sign here, okay? For the leftmost state here, okay? So this is the state that the max player designed to place the X symbol at the top left-hand corner, okay? And if really the max player really goes through this step, then the min player will be forced to start with this state, okay? And under this stage, the min player can do all these sorts of operations, okay? So as you can see here, in the child node of the leftmost node right here, we are actually trying to list out all the possible outcomes right after it, okay? So if the max player goes with putting the X symbol at the top left-hand corner, so the game will becomes like this, okay? And after the game becomes like this, the min player will have no choice to work with this state. So there are 8 total possible places that we can put the O in. For example, we can put you here, 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 and here, okay? There are 8 total possible combination. So what we do is that we also list them all out. Okay, we also list them all out as the child node of this node. Okay, and then the game will go back to max player. Okay, and for each node here, we will actually generate the possible outcome as well. Okay, so this whole search tree is to actually generate all the possible outcomes after a player make a move. Okay, it keeps on doing that and form a tree. Okay. 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 So the next question is, so when we reach the end, then we will actually know the score. And after knowing the score, then we can backtrack and we can actually know what is the choice, what is the action of the choices that the max player at the beginning will make. Okay? Okay. So the whole idea of the search tree is very similar to the decision-making tree. We just try our best to enumerate all the possible decision-making combination of decision-making that we can do, and then we select an output that we want, and then we backtrack. Right? But we can do it in a more clever manner. Okay? So as you can see here, this is a simplified version or is a very simplified game, okay? And in this game, I will make it more clear. Wait. Okay, so as you can see in this tree, okay, we actually have two layers. We have one max player and then we have one min player and then we end the game. Okay, so in this game we actually have two turns. Okay, the max player make a action and then the min player make a response and then the game ends. Okay, so now we create a tree like this. Okay, the max player actually can make 3 different moves. Okay. And after making 3 different moves, the max the game will become the state B, C, and D. Okay, B, C, and D. Okay, B, C, and D. And in the perspective of the max player, in order to make decision, okay, what it need to know is to know the final outcome of the game at for B, C, and D. So we want to find a way to actually calculate the final outcome of the game of state B, state C, and state D. Okay? Okay. And this is actually another way of thinking, another angle of thinking. Okay? We can totally generate the whole search tree and then go through all the outcomes and then choose one. Or we can actually do this thing in another manner, okay? We can do this in a recursive manner, okay? So let's take a look on this tree, okay? The max player at A would actually can actually make 3 moves, and these 3 moves will generate the states of B, C, and D. Okay, so in the perspective of the max player, as long as it knows the utility score of B, C, and D, then it can make the decision already. Okay, then it can make the decision already, right? So if given the maximum player at the state A can have 3 different moves, and the 3 different moves will generate state B, state C, and state D. And for the state B, state C, and state D, their score is unknown right now. But if we are able to find out the score of the state B, state C, and state D, then we can decide what action the max player will make. Okay, and we can even calculate the utility score of the A as well. Okay, so how we can know the utility score of B, C, and D? Very simple. We just take a look on each state and we calculate. Okay, so now we consider the B. The B now is the mean player's turn. So because it is the mean player's turn, okay? So it will of course still need to if the state B is the mean player's turn, and the mean player in the state of B can have 3 different moves, okay? And these 3 different moves will reach the terminal node, okay? The outcome of the terminal is 99, 91, and 30. Okay? So based on the our understanding on the mean players logic, it will always try to go to an action that can lead to a smaller score. So for the B here, the score should be 13. Okay. And similarly, for the mean player at the state C, it will also try to find the minimum score. So the score is 8. Similarly, for the state of D, okay, you will try to find a minimum score. So the score is 23. Okay. So this is one thing you should know about the search tree. When you are working with the search tree, if you come across a state, okay, listen to me very carefully, okay? I'm trying to talk about some rules you can remember. You can actually recite, okay? So if you come across a state that you don't know the utility score, it is very simple. What you need to do is to find the utility score of all its child nodes, and then after you find the score of all the child nodes, you try to check out what is the turn of that state, okay? So for example, the state B is the turn of the mean player. So, and we also already know the utility score of each children node that is 99, 91, and 13. So the state of B belongs to the mean player. So that means that the mean player at the state of B will choose the minimum action. So it will definitely choose 13. So the outcome of the game at the state of B is 13, okay? Because the state of B belongs to the mean player, so it will always prefer action that will minimize the final outcome of the game. And because the child node of B is having a score of 99, 91, and 13, so it choosing the minimum one, it will be 13. Okay, you just remember these 2 rules. The first rule, if you come across a node, you don't know the utility score, just do the following. First, you check out the child node to find the score. Okay, once you get all the score of the child node fixed, then you check out which player the state belongs to. Okay. And for example, if you are finding out the utility score of the state of A, okay? To find the utility score of the state of A, you need to figure out the score of the utility score of B, C, and D. Okay? But you now don't know what is the utility score of B, C, and D. So what you will do is you will try to figure out the B, C, and D utility score one by one. Okay? And for the utility score of B, you have the child node of the B is all terminal, and the utility score can be calculated directly with the utility function. So I just get the utility score, I choose the minimum one, and then and then assign it to B, and that will be it. Okay. And after I do so for the C and for the D, I can do an overall comparison of B, C, and D utility score. And because A state is the max player's turn, so it will choose the maximum utility score out of B, C, and D, and it is 23. Okay. And what if the situation is more complicated? You just do the same. Okay, so please look up here. In this diagram, we have a more complicated search tree, but the overall idea is the same. Okay, so if I want to know the utility score of the state of A, what I will need to do is to calculate the utility score of B, C, and D, right? Because the child node of the A node is B, C, D, okay? But for the state of B, the E and F is unknown, okay? So I will need to figure out the score of E and F first, okay? And for the E and F, okay, their child node are all terminal node, so we can just evaluate the score of E and F directly. We don't need further referral, okay? So for the node E, okay, for the node E, it has a terminal node of 34, 62, and 36, okay? And we also know one thing is that the upper red triangle is the max player. Okay, so E is the max player's turn. E is the max player's turn. And the state of E has the 32, 60, 34, 62, and 36. These three terminal nodes. So what we want to do for E is to find the maximum value among all these three values. Okay. Okay, so the utility score of E should be 62. Should be 62. Okay, should be 62. And we can do the same for the F as well. Okay, so when we work on F, okay, we are still following the same logic. We check out all the child nodes to see if one of them is unknown. If one of them is unknown, and all the child node of the F is known because all the node of the F is terminal node. And as a result, we proceed to the next. We check out which player this state belongs to. This state belongs to the max player. So we will take a maximum between 40, 72, and 7. So as a result, the utility score of F is 72. Okay. So right now, you will figure out the utility score of the child node of B is 62, 91, and 72. Okay. And then you already figure out all the child node score of the node of B. Okay. So now you can go and figure out what is the score of B. Okay, 64, 91, and 42. We need to figure out whether we need to find the maximum or the minimum. And because the state of B belongs to the mean player, we can identify according to the symbol. So at this stage, we can actually say to figure out the score of B, we need to take the score of the child of B that is 62, 91, and 42. And we take the minimum of them, and the score of B should be 62. Okay? 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 So we can repeat this whole process again and again, and we can solve the whole search tree. Okay? Okay? Just remember these two rules. Everyone, really, please remember these two rules. Okay, I hope you can remember these two rules. The first rule is that if you want to find the score of a node in the game search tree, the first rule is you go check out all the child, go and check out all the child and figure out the score. Okay, figure out the score. Okay, if the score of your child node is unknown, then you go deeper. Okay, so in this case, okay, originally E and F we don't know its utility score for us to solve the B. So no problem, we just solve E and F first, and after we solve E and F, we solve B. Okay, okay, and after we figure out the score of all the child node, we take a node on the node we want to work on and check out what player it belongs to. Okay, so in this situation, the state of B belongs to the mean player, so we just take the score of the child node and then we take a minimum value. Okay, and then we take this minimum value A assigned to B. Okay, the underlying logic is that we assume the max player and the mean player would follow its objective strictly. Okay, because the E is the turn of the max player, the max players in order to win has to maximize the score, so it will choose an action that will make the score become largest. Okay, so as a result, for the state of E, the score will always be 62 if the player is being logical. Okay, okay, and also for the state of B, okay, in order for the minimum player at the state of B will win, it will choose an action that will minimize the score. And among E91 and F, okay, the state of E having the value of 62 is making the score the smallest, although it is still losing, but it's not losing as much as the other choices. So it will go to E. Okay, so as a result, the score of the B is 62. Okay, so any questions? Any questions? Any questions? This is the whole logic of the search tree. Okay, even though you may not able to you may still not able to fully understand the search tree, but I still hope everyone remember these two rules at least. Okay, okay, I hope you understand what I'm implying here. Okay, okay, so please just remember these two rules at least. Okay, so any questions? So any questions? Two rules. We just remember two rules. If you come across a node, you don't know the utility value, just remember two rules. The first rule is you try to figure out the utility score of all its children nodes, and then check out the owner, check out which player this state belongs to, and then you choose the maximum or the minimum utility score of each children node based on the player it belongs to. So these are the two rules you must remember. Okay? Okay? And you may also observe one thing. The overall process of figuring out the value of the tree here is actually done in some sort like a recursive call. In order to know the utility score of A, we break it down into the utility score of B, C, and D. And in order to know the score of know the score of B, we break it down to know the score of E and F. Okay, we constantly break down the problem we want to solve into some smaller problems, and up to the point we cannot divide further. For example, in E, we cannot divide it further because all the nodes below the E, all the channel of the E are terminal node. Okay, so at the moment we cannot further divide our problem, we then use our base case to calculate the smaller problem, and we use the result of the smaller problem to calculate the result of the bigger problem. So in fact, the search algorithm here, the tree search algorithm here, is using recursive call. Okay? 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 Understand, right? Understand, right? Okay? And this is actually reflected in our source code, okay? And I already said so in the previous lecture is that in our exams there will not be any programming questions, and we don't have I'm afraid that we don't have enough time to cover all the materials needed for exams. So I will skip the algorithm the source code detail discussion right here, okay? But I will at least talk about the general idea, okay? So in the max value and the mean value function here, the max value and the mean value function is to try to evaluate the score of the states belong to the max player and the mean player respectively. Okay, so in these two algorithm, for the max player, what it does try to do is to check, first of all, check if the state is the goal state. If the state is the terminal state, then we don't need to do anything further. We just call the utility function of the problem and just calculate the score, and that's it. Very simple. But on the other hand, if the state we are working on is not a terminal state, what we will do is we will generate all the child nodes. And after we generate all the child nodes, we try to figure out the utility score. Okay? But because you are now the max player and your child node will belong to the mean player, because the game will be max player and the mean player and the max player and go on. It goes on intermittently. Okay? So that is why under max player we will call the mean player inside this loop. This loop is to go over every child node of the node that we are having. Okay? And when inside the loop, we keep track on the actions and we keep track on the score that is maximum, and we keep track on the action that can cause this maximum maximum outcome. Okay? Okay. So any questions? Any questions? Any questions? Any questions? Okay. And on the other hand, for the mean player, we also do the same, but rather than calling the mean value in the function, we call the max value. Because the mean value, because the moment we call the mean value to evaluate a state, that means that the state belongs to the mean player. And the state belongs to the mean player, the next state will be the state that belongs to the max player. Okay? So that is why in the mean player we'll call the max value function. Okay, so you can see this trend is that the max player is calling the mean player, and the mean player is calling the max player, and the max player is calling the mean player. Okay, the max player and the mean player are calling each other in an interleaving manner. In Cantonese, we can say as 梅花間竹式. Okay. Okay. They are calling each other in an interleaving manner. Okay. And here is just a dry run of the algorithm, okay? Okay? And what that is, or I will not go through this dry run in a detailed manner, but I hope everyone can observe one thing is that for now we start with S0 as the max player. And in order to evaluate S0, you need to evaluate S1, S2, and S3. And when you are evaluating S1, S2, and S3, you don't get the result on S1, S2, and S3 at the same time. Okay? One thing I hope everyone catch here, okay? Okay? When you are evaluating the score of S1, S2, and S3, you don't get the result at the same time. you evaluate S1 first, and then you evaluate S2, and then you evaluate S3. Okay? And when you are evaluating S1, what you will do is you will expand, you will try to find out the next state of S1. So now we have T2, T1, T2, and T3. And the evaluation of T1, T2, and T3 are not done at the same time. We do the evaluation of T1, T2, and T3 sequentially as well. Okay? You may ask me, Professor, so now we have multi-core CPU, so why we do things in this manner, okay? This algorithm is designed in the age that computer only have one CPU, okay? So that is the reason why we evaluate all the score of this node in a sequential manner, okay? We don't have parallel computing right here, okay? I understand that we can do parallel computing, but this is not a situation we are trying to do it, okay? We are talking about the simplest case. And as you can see here, T1, T2, and T3 are being evaluated sequentially, okay? And after we get the score of T1, T2, and T3, then we can find the score of S1. And after we finish the S1, then we'll calculate S2 and S3, okay? Very simple stuff, okay? But I hope you will discover one thing here is that when we want to find the utility score of a state by evaluating its child node, the evaluation of the child node is not done in the same time, okay? We do it sequentially one by one. Okay? Okay. So this is vital. This is vital feature. Okay. So one thing I hope you understand is that, or maybe I will just use this example. Okay. So one thing I hope you understand. Okay. Okay. So now let's consider the search tree right in the background, in the screen, okay? So as you can see here, we just finished the evaluation of B. Okay, everyone, we just finished the evaluation of B. Okay, so now the score of the state of B is being an information we can exploit. Okay, because we are evaluating the state sequentially, we evaluate B first, and then we evaluate C, and then we evaluate D. Okay, so that is one observation I hope everyone here can observe. The result of B, C, and D do not appear at the same time. The score of B appear first, and then the score of C is evaluated the second, and then the score of the state of D is at the last. Okay? Okay. That is the state of B, C, and D, they are not evaluated and they do not get the result. We do not get the result of them at the same time. Okay? So that is something we can play with. If we know the score of B first, then we can use the score of B to assist with our calculation of the C and the D, right? 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 Anyway, is that logical? Up to now, is that logical? Because we evaluate B, C, and D sequentially. So after we calculate the score of B, the score of B becomes an information that is available to us, and we can use it to assist with our calculation of C and D. Makes sense, right? This logic, this idea makes sense, right? So the next thing is how it can be used. So now let's consider this, okay? Imagine this. Maybe I will draw draw a triangle to I will draw something to make sure I get the message delivered, okay? Okay. So now let's consider we are evaluating C, okay? We just finished the evaluating the state of B and we are evaluating the state of C. Okay, we are evaluating the state of C. And when we are evaluating the state of C, we need to get the utility score of all the child node of the state of C, right? Okay. If we want to know the utility score of C, we need to calculate the score of all its child node, right? So now for the state of C, we start with the leftmost utility score, okay? We start with the leftmost terminal node, okay? And the leftmost terminal node of the state of C is X. Okay, is the state of X. Okay? Up to 90 questions. Up to 90 questions. Up to 90 questions. Okay? And the 90 and 37, we still don't know their score yet because we still haven't evaluated that. Okay? The score of the child node of C is evaluated sequentially, and we start from the left to the right. So the moment we evaluated the left terminal node, we only know the left terminal have the score of X, and the other two terminals are still not known to us. Logic, right? Okay. So let's consider this. The state of C belongs to the mean player, right? A mean player has a logic in mind. It will always choose the minimum route. It will always choose the nodes that have a minimal cost. As a minimum score, okay? So he found that after the evaluation of the of the leftmost state, okay? Of the leftmost terminal node, okay? The leftmost terminal node is given a score of X. So that means that if the rest of the terminal node of the C is given a score higher than X, the utility score will not choose that, right? Okay. Let's find out how this. Now, the remaining child node of C is having a score larger than X. Will C choose other nodes or they will stick to X? Okay. So for example, right here, I give you that the next two terminal node is 19 and 37. So would the child node, would the state of C, will the state of C chooses the other terminal other than X? Okay. So now now let's consider this, okay? The state of C is we are trying to figure out the utility score of the state of C. And the state of C belong to the mean player. And we now first evaluated the leftmost terminal and the score is X, okay? And now I'm asking a question. If the rest of the terminal node is larger than X, will the mean player as is choose other terminal, but rather than fixing on X? Okay, it will still fix on X, okay?
Cannot see. Not ignore.
Let's do the imaginary discussion. Let's do an imaginary discussion. If case one, if the terminal node right after X being evaluated have a score larger than X, will the mean player choose other terminal rather than it will stay at X? It will just stay as X, okay? Because the idea is very simple. The X is smaller than the other terminal nodes in our imagination. Okay, in our emergent condition, okay? And case two, imagine all the terminal nodes right after X have a smaller cost, have a smaller score, then the C will choose that, right? Okay, so no matter what, the moment the mean player at the state of C have evaluated the first leftmost node, that is X, if we can establish a upper bound like this. Okay, less than or equal to X. Okay, makes sense, right? Anyone, it makes sense, right? The logical deduction makes sense, right? Anyone at the back, it makes sense, right? The logical deduction makes sense, right? Okay. So we deduce the after the moment the mean player as C have evaluated the leftmost node X, we can establish this bound. That is a upper bound. Okay, it is bounded by X. And we also know that the utility score of B is 30. Okay, the utility score of B is 30. Okay, but C, no matter what, it will have a utility score less than or equal to X. So my question is that, will the max player even consider C? Will the max player even take a look on C? The score of B is 13. The score of C is bounded by X. That is established by us.
What max plus then you will ignore C.
Yeah, it will ignore C no matter what. Right?
Because you are here and the C is here.
Yeah. So the logic here is that the remaining two child nodes of C, we evaluate or not, it doesn't matter. Right? It doesn't matter. No matter what value you have, for the two child nodes of C, the evaluation of the search tree will not be affected by it. Okay? The moment you evaluated the leftmost node of the state of C, you already established a upper bound for the score of C, and as a result, the rest of the two and the upper node upper bound here is useful when compared to the original when compared with the best case scenario of the max player. We can be sure that the max player will never choose the C anyway. Okay, so the rest of the child node of the state of C doesn't matter. It doesn't affect our results. So do we need to calculate them? Okay, we can just throw them away. We can just ignore them. Okay, we can just skip two calculations right here. Okay. So this technique, if you apply it throughout the search tree, then its purposes is to use logic deduction to skip some branches and to speed up your calculations. Okay. And this technique, we give it a name and we call it as pruning. Okay. Okay. And one thing I hope everyone understands is that this pruning technique is very, very important. Okay, it's very general. Okay, in our whole logical deduction, we are working with a generic search tree. We are working with a search tree that is generic and do not attach to any kinds of checks. our deduction on this search tree can be the search tree of any chess. Okay, we extracted the detail of the chess game away from the search tree. So this technique is widely available and widely suitable for different kinds of chess. Okay. Okay. So this is why this technique is very important. Okay. And essentially, and you may ask is okay, for Professor, you speak so much during the lecture, and I don't have enough time to take the notes, okay? Or even if I listen to your recording, my English is I just don't understand your English that I cannot take notes, okay? Don't worry, I get this covered, okay? You can act. In fact, I'm just actually reading the same content as the PowerPoint. Okay, I've actually included all the details that thing in the PowerPoint. You just take a look on the PowerPoint and you can read it. Okay. 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 So so this is how you can get referred to. Okay. I've included all the discussions in text. Okay, in detailed text in the PPT. Okay, so you can follow it. Okay. And here are some properties of the pruning you should know. So first of all, pruning will not affect the final result. Our pruning is fully based on our deduction, our logical deduction. As long as this logical deduction makes sense, then the pruning will not be wrong. Okay. It is purely based on logical deduction, but not by approximation. Okay, we know that this branch is not necessary because we logically deduce that it is not necessary. Okay, and in fact, in the future, you'll be working on a lot of algorithms. Okay, many researchers have developed algorithms to speed up the speed of an algorithm, or to speed up the efficiency of an algorithm. Okay, and to increase the efficiency of an algorithm. And most of the thing they done is to do things like this. Okay, using logical deduction and doing some calculation such that they can skip even bigger calculations. Okay. And if you have heard about the news, okay, actually the Google engineers have developed a new technique that can reduce the memory consumption of large language models by very big margin. Okay, so this is the true intention why we teach algorithms, why we allocated one class to talk about algorithms. Okay, in the future, okay, if you are working in state-of-the-art large language model research, then your research will actually go back to the basics on the algorithms. Okay. Okay. So any questions? Any questions? To be honest, I truly understand many students really think this class is very boring. I understand many students actually think this class is very boring, and they think that this class material after they learn, they don't have many places they can use. But I hope everyone can understand that the ultimate objective of this course is not to teach you algorithm, it's to train you have the ability to understand and appreciate how algorithm will help you to write better program. Okay, and that is the ultimate technique. And that is the ultimate objective. Okay, in the future, I don't think you will need to write min-max algorithm or alpha beta search. Okay, with your bare hands. Okay, but through the lecture time, I hope I can teach you the importance of algorithm design. With simple logic, you can actually carefully avoid the unnecessary calculation and speed up your algorithms. Okay? And this is very important when you're writing a very big piece of software. When you're writing a very big algorithm, if you're able to save some time there, save some time over there, then gradually you can you can improve the efficiency of your algorithm a lot. Okay. And I also forget to talk about one thing is that okay. So let's consider the last branch. Okay. For the last branch, okay. The if we take a look on the D, of the state of D, the state of D belongs to the mean plane. Okay? So when it takes a look on the first left node, okay, the value is 52. So using the same logic we talked about, we can deduce its bound is less than or equal to 52. Okay? But then 52 is not smaller than 13, so we cannot be sure that the max pair will not choose D.
Then you need to check.
Then we should check the rest. Okay. So for the next one is 70, 79. So we don't need to change this bound. Okay. And finally, if we check out the 23, then we check all the child node and we can establish the real utility store of D and 23. Okay. And then that's it. Okay. So sometimes the pruning would not work. Okay. It actually depends on the branch ordering. Okay. 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 If okay, if we rearrange the ordering like this, if we reorder the branches ordering like this, okay, then okay, then the score of the leftist branch of the A is X. Okay. Then if we evaluate the state of B and D right now, the pruning will not work. Okay.
Yes, it needs to check everything.
Yeah, you need to check F.
That's it.
Okay.
Yes.
So let's go over it. Okay. For B, okay. For B, okay, is initial bound is less than or equal to 99. Okay. And then next one will reduce it to less than or equal to 91. Okay. And then next one, okay, you get 13. Okay. So yeah, so you check everything. Okay. Similarly for the D. Okay. Okay, so 32, 52, 97, 79, and 23. Okay, so we will get 23. Okay, so just swapping the branches, reordering the order of the branch will make the pruning not able to work. Okay, so this example clearly show one thing, right? Clearly show one thing that is very important. Good move ordering improve the efficiency of pruning. Okay, I show it to you already. I use an example to demonstrate for you already. Okay. Okay. And with perfect ordering, the time complexity will be equal to OB powered by M divided by 2. Okay. Originally is the big O of B powered by M. Okay. So essentially, we reduce the scale of the depth variable by 2. Okay. So as a result, we can double the size of the depth. Okay. So using pruning, you can easily double the depth of the search, and as a result, your search algorithm will become far better. Okay, assuming your order is perfect. Okay. Okay. And essentially, this is one crucial factor when you are trying to design algorithms. Okay, if you are trying to design or improve an algorithm, one of the ways to make your algorithm run faster is to avoid unnecessary calculation. Okay, but anything comes with a trade-off. Okay, so if you check a calculation need to be calculated or not is too complicated, then the cost is too large, then everything will be the same. Okay. Okay. So any questions? So any questions? Any questions? Any questions? And one thing I hope everyone here understand, there is a trade-off, there is a cost of doing everything. When you are doing the filtering, if you are selecting computation that is not necessary to do, you will also need to do extra computation to achieve it. If your extra calculations is taking more time than doing the original calculation, then you please just do the original calculation. Okay. 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 There is maybe I will, but maybe I think about this. I have example. Okay. So for example, if I have a product that I can put for example, now I'm living in Hong Kong, okay, and I have a product that I want to buy and it is selling at $100, okay, and that product is doing a 90% discount, but the store doing the 90% discount is at Tuen Mun. Okay, so for me to go to Tuen Mun and buy it and then get back to Hong Kong, the cost of the transportation will override the cost I saved on the discount. So I will rather buy at Hong Kong. Okay, makes sense, right? Okay, so this is one thing you need to consider it as well when you are when you're thinking about how to speed up an algorithm. The calculation you do to make sure a big complicated calculation can be avoided should be very simple. Okay, otherwise it doesn't worth it. Okay, there is a trade-off of everything. Okay, such as if you can buy a product at $100 right next to your doorstep, then it is much better to go to other places with a very high traveling cost, but getting a little discount on the actual price of the product. Okay, so any questions? So any questions? Any questions? Okay, so now I'm very lucky that today I can finish all the material that is required for you to do the assignment 2. Okay, I will release the assignment 2 next week. Okay? And I've already covered all the material you should know up to how to do the assignment 2. Okay, in the assignment 2, we will cover A-star search, we will cover pruning. Okay. Okay. So any questions? Any questions? Any questions? Okay. And A-star search can be generally applied to more complicated search tree, but I will leave it for your own thinking at home. Okay. And here is the algorithm here is the algorithm implementation of the alpha and beta pruning. You may ask this, Professor, so why is called alpha and beta pruning? The reason why it's called alpha and beta pruning is that in the actual algorithm implementation, we use the alpha and the beta as the argument of the algorithm to carry along the best choices of the max player and the best choices of the min players. Okay, so when you are doing the pruning, in order to know the tool here, in order for you to know the pruning can be done at this stage, is that maybe I will choose my original one. Okay. The moment you know you can do the pruning right here is that you know that is a better choice of the max player that is called 13, right? And the better choice of the max player 13 that is transferred to here when you are evaluating the state of C is done by the argument parsing. Okay? Okay? So the alpha and the beta are used as the argument of the recursive function to transfer the information of the best choices of the max pair and the best choices of the mean pair right now. Okay, and that is the reason why it is called alpha and beta pruning. Okay. But in this course exam, we will not go into the technical details of the algorithm. Okay, so I will not explain the details of the implementation right here as well. And also the dry run, I will not go for it as well. Okay. So any questions? Any questions? Okay, but I still put the notes here so you can go for it at home. Okay, but because of the time constraint, okay, because of time constraint, I still have one more lecture to go before you take the exam. So I will skip the material from now on. Okay. And so now I guess everyone is here finally, so we can talk about the exams. Okay. For the examination announcement, you don't need to take photos. Okay, I myself is also clicking on the Moodle's PDF and showing to you. Okay, so please don't take photos. Okay, just look at the Moodle and get the PDF on the exam announcement. Okay, so for the exam, you will have two parts: 15 MC questions, 4 short questions. Okay, you need to do all the questions. Okay. MC question is similar to the previous assignment. Okay, give you more than 4 choices, choose one that is correct. Okay, more than one answer, more than one choice means wrong. Okay, and you need to do all the questions. Okay, you can bring your calculator, and you cannot bring other electronic devices, and you can bring in one A4 double-sided page of reference note. Okay, I don't care how you prepare, you can print it, write it, or whatever. Okay, as long as it is one page double-sided. Okay, and I hope everyone please do it on your own. Okay, because doing the preparing the reference note by yourself is actually a process of preparing yourself for the exam as well. Okay, and you are reminded of the necessity of clearly and orderly presentation in your answers. Very simple. Make sure the thing you write can be understandable by every human Joe, and I can read it, and I can understand it, such I can give marks to you. Okay, don't write me something that normal human being cannot understand. Okay, the logic is that I cannot give you marks unless I clearly see what you are writing. Okay, if I cannot even see you are writing, sorry, I cannot give you marks. Okay, so this is the logic why you want to keep your answer simple, clear. Okay, and also I understand that some Chinese mainland students, you are not used to using correction tape, because in Chinese mainland the examination there doesn't allow you to use correction tape. But please, if you can, use correction tape. Don't just to cross out the answer that you write wrongly and then use an arrow to point to whatever places and force me to trace your answer. It is very, very difficult to do. It is actually very difficult for a teacher to keep on tracing your arrow. Right?
Or use a pen.
Okay. Pencil is generally to be honest, I will avoid using pencil because there is a risk that if we are packing or transporting the paper may get rubbed up with each other, the pencil trace may get fade out. Okay, so for your own sake, I think it's better to use pen, okay, rather than pencil. Okay, because pen have a longer lasting trace rather than pencil. Okay, if you use pencil, as long as the pencil trace is readable by me, I can still give you marks. The overall idea is I can read it clearly. If I cannot read it clearly, I cannot give you marks. Simple as that. Okay. And regarding the exam, okay, once again, I said this almost like several times already around these two or three lectures. Low programming questions, and low programming questions, okay? Important things you need to repeat it 3 times, okay? Low programming questions, okay? So although in past paper, if some student already share past paper, there is some question that you will need to fill in the blanks as programming question. But this year, we simply don't have any programming questions, okay? Okay, so you don't need to prepare for it, okay? And the question style of the examination paper will be similar to the written assignments again. So I hope everyone can really can really try your best to do your assignment on your own and do it carefully and do it very carefully such that you can better prepare yourself for the exam as well. Our exam is similar to the assignment style. Okay? Okay? And the exam will cover lecture 1 and lecture 1 to lecture 6. So in fact, we still have one more lecture we need to go through. So this is why you see that I am rushing my time right here. Okay?
So excuse me, the multiple symbols questions, is it through that?
Lecture 6.
Okay.
Lecture
Good.
6.
Good.
Okay? Lecture 6. So that is the reason why if you are checking out the past paper, you can see some logic related questions. Because in lecture 6, we'll actually talk about logical agent. Okay? So any questions? Any questions? If you do not have any question, then this is the end of today's lecture. Okay, and don't worry, this PDF will be on the Moodle anyway. You can take a look on it all the time. Okay, okay. Just because the reason why I want to announce it here, just to make sure everyone knows this message. Okay, and I will end the recording here. And this is the end of today's lectures. Okay.